Good morning, everybody. Today I will be presenting to you on electromagnetic flux. There are some things that we need to know before talking about electromagnetic flux, such as the right-hand curl rule around a current carrying wire. So the right-hand curl rule, RHCR, is a very simple rule to follow, and there are two very important steps. So the first step is to point your thumb in the direction of current flow, as shown in the image. And then step two is to wrap your fingers around the thumb to see which direction the magnetic field is in, as shown here. If needed, you can grasp a pencil in the palm of your hand and curl the fingers around it to easily visualize. So now let's get into magnetic flux. Magnetic flux is the amount of magnetic field lines through a certain area, or in this case, a wire loop. The symbol slash units, the symbol is phi, and its units are in Webers or Tesla meter squared. The maximum flux is when theta is 0 degrees, and the minimum flux is when theta is 90 degrees. On the right, here's the magnetic flux formula. Phi is equal to BA cosine theta. So the magnetic flux is phi. The B is magnetic field in Teslas. A is the area in meters squared. And theta is the angle between perpendicular vector to the area in magnetic field in degrees. Another important law that we need to know is Faraday's law. Faraday's law states that a change in magnetic flux over a period of time t creates an electromotive force or voltage. The number of coils in the wire N affects the total voltage produced as well, as shown in the top right. Using Ohm's law, E is equal to IR, we can find the magnitude of the total induced current, I, which requires basic algebraic manipulation. Essentially, just substituting the value of E in the top for IR, and then dividing the uh, Faraday's law by the value of R. Okay, now I'll be showing you a simulator to show the effects of factors that affect magnetic flux. All right, so we're at the simulator right now. So the first thing that I'll show you is how the flux changes when you move the wire, the bar magnet into the loop of wire. So if we move it slowly, there's not much flux increased. If we move it fast, however, there's a lot of flux induced, right? The area of loop, if you increase a loop area, the flux increases. If you decrease a loop area, the flux decreases. I can't show it to you because the simulator doesn't allow me to. Um, but I can show you the number of loops increasing. So if we increase the number of loops, there's a lot more flux induced. And lastly, if we decrease the strength of the bar magnet, let's say to 80%, 75%, the magnetic flux will decrease. And then finally, if we were to pull the bar loop at an angle, such as a 45-degree angle, there would be less amount of magnetic flux because there's less field going through the wire. Feel free to take notes based on question number 4 on the loop on this slide. Okay, another thing that we need to know is a right-hand current curl rule, or RHCCR. It's essentially the same exact thing as the RHCR, but there are two modifications. So the first modification is instead of the thumb as the direction of current flow, the thumb is the direction of the induced magnetic field. And the second modification is to wrap your fingers around the induced current instead of wrapping your fingers around to show the direction of the induced magnetic field. And you can always grab a pencil in your hand and curl your fingers around it to easily visualize. Lenz's law. Lenz's law is an application of Faraday's law. It states that the direction of induced current is opposite to the changing magnetic flux. To determine the direction of the current, use the right-hand current curl rule, or RHCCR. So there are a couple conditions that we need to know. Changing magnetic field strength, changing area, changing theta, and changing the value of N. So let's start off with changing the magnetic field. So changing the magnetic field induces current due to the changing value of B in the magnetic flux equation, according to Lenz's law. So increasing the magnetic field increases flux, which leads to induced field to be in opposite direction. Very important. Increase in flux, opposite direction. And you can calculate the direction of induced current using RHCCR. Decreasing the magnetic flux leads to the inducing field to be in the same direction. It's very important to realize that a decrease in flux is the same direction, and you can calculate the direction of induced current using the RHCCR as well. Changing area. So changing area is essentially the same thing as changing the magnetic field, except instead of changing B, you change A. The conditions of increasing area also are the same. Increasing flux, opposite direction. Decreasing flux, same direction. And you can calculate the direction of current using RHCCR as well. Same thing with rotation. Inducing current, except you're changing the value of theta instead of A or B. Increasing angle is increasing flux, induced field in opposite direction. Decreased flux, same direction, same thing. Okay, here's something that's a little bit different, but it's not very hard. Inducing current as changing the value of N in Faraday's law, not the flux equation. So essentially, this changing loop number works only with changing the first three variables: angle, field, and area. So you need to change one of those variables first and then changing the value of N. So increasing loop number increases voltage after the initial change of A, B, or theta. And decreasing loop number is a decreasing voltage after changing A, B, or theta. All right, so here's a demonstration that I've provided for you. It's essentially the same as the virtual demonstration, except in real life. Okay, so notice how in the demonstration that I provided, when I move the magnet into the loop of wire, there's a flux induced. But when I leave it in the loop of wire for a little bit, there's no flux induced because the change in flux is really what produces the increase in voltage. Okay, so here are some multiple choice problems for you guys to attempt. Please, I have worked out solutions on the next slide, but please don't look at them before you try these out. These are very good problems to help you solidify the concepts. I made them myself. Thank you very much for listening to this presentation. I hope you have a great rest of your day.